All right. So let's start again. It's lecture 2 for the class. We start with a review. And so the review has only one slide because there's only one important thing to remember from the first lecture, which is what we call the fundamental theorem. So I'm assuming that everyone read the lecture notes corresponding to these, maybe watched the video, maybe looked at the whiteboard notes. And so I'm not going to introduce all the necessary notation and everything. So just give you a high-level overview, a bird's eye view, if you want, of what this lecture is about. And for that, it's just really easy to say. There is this fundamental theorem that I like to call fundamental. I think I saw it, other people calling it fundamental theorem for MDPs. Basically, this theorem says that the optimal value function is the fixed point of the Bellman optimality equation. And if you take any greedy policy with respect to the optimal value function, then this policy is going to be an optimal policy. So these are the two parts of the theorem. And so this theorem, I gave a proof of it. And when giving the proof, we only did everything for finitely many states and actions. And this is also for the discounted case. Well, let's see whether I can write stuff here. Let's see. Huh. So it's for the discounted case. So in these lectures, we are mostly going to look at discounted MDPs. And the reason for that is because they are sitting somewhere in between the finite horizon case and the average cost infinite horizon case, or a total reward undiscounted case. So it's kind of like maybe a little bit easier than the other cases, fewer complications, easier in that way. But there are some complications that do not arise if you only look at finite horizon settings. Later on, we're going to look at the finite horizon setting quite a bit as well. So we sort of give up on the discounted case to simplify things. But so this theorem is stated for the discounted case, but you might wonder about, like, is it going to be true for these other cases? And so that's a very good question. And it turns out that the discounted case is super nice. The proof is not too hard. Well, first of all, what's really special here about the way I do this theorem, or like this theorem is presented, is that V star, the optimal value, is defined with respect to all policies, including history-dependent non-stationary policies, not just stationary Markov policies. What you usually see in when people are presenting stuff for MDPs, they kind of skip this. But the whole point of this theorem is that, well, these non-stationary, non-Markov policies do not add anything to the generality. But before you prove this, you don't know. So this theorem is really partly about that. But you can state it and prove a theorem for just the stationary Markov policies. That's much easier to state and prove. Or the non-stationary Markov policies, that's also much easier to state and, well, you state it. It's the same theorem. but the proof is somewhat shorter. But I think that like here, it's really, I think, a nice feature, and an important thing to know, that if you're really in a Markov decision process, you don't have to remember the history to be able to act optimally. And this is the theorem that tells you that. So now I try to first to prove this theorem without with some really high level arguments. But the only argument that I found elegant and short enough was through going through this discounted occupancy measures, which are interesting on their own. And for the discounted occupancy measures, there is this other statement that you can prove that shows that. So there it is. Occupancy measures over state actions or states. So occupancy measure just means like, what's the total occupation for a given state over trajectories induced by a policy if you're starting the policy from some initial distribution. The same with state actions. And the argument that I found, which seemed to be the shortest and most elegant, is going through this state occupancy measures, and it's really interesting on its own. So what you can show is that if you're taking policies, any policy, and then you look at the discounted state occupancy measure underlying of this policy with respect to some initial state, you can always find another policy which is a stationary Markov policy, pi prime. So it's a memoryless policy. Ah, the graphics is not the best, but whatever. I hope you can still read it. So you can find for every pi and mu, you can find a pi prime memoryless policy such that the occupancy measure is reproduced. And this is why essentially the policies that remember the past or try to use the time step do not help at all, because they do not help in generating a richer class of state occupancy measures. So in a way, the state occupancy measures are fundamental. They kind of capture everything about the policies. And then here what we find is that these memoryless policies generate the same set as the bigger set of policies. All right, I saw that there was a question. Haha, okay. So if the reward function was also a function of histories, none of this stuff would hold. Well, okay, so good. So the state occupancy measure itself, of course, is independent of the reward function. And the reason we like it, it's just dependent on the policy and the dynamics, the transition dynamics of the MDP. So the reason we love it, and it's really nice, is because it kind of separates the reward out, right? Like the value can be expressed as inner product between a state occupancy measure and the reward function, and that is just like super useful. So this holds for the reward functions, which are functions of state actions. There were some questions later on which are asking questions about, okay, what if the reward function would have other properties? Let's get there later. But here, if the reward was dependent on the history, then you wouldn't have a Markov decision process, right? So it's really important that in a Markov decision process, the reward also don't depend on the history, right? Like, so when we define this Markov decision process, you can approach this in two different ways. You can look at Markov decision processes as the collection of all possible probability measures over trajectories that are induced by the possible policies. So it's like that is one object. Or you could view it as like, oh, we just give this transition kernel, and that defines implicitly this other set. So this other set is kind of redundant, and like, and of course, you can extract the transition probabilities from it. And but the point is that if you have this distribution over the trajectories that only depends on this Markov kernel, then after that you could, yeah, indeed put no stationary reward or history dependent reward. That would be different. There you could also try to deal with that by defining occupancy measures which also are sensitive to time. Because when you're taking this expectation over the return, right? Like the expectation commutes with the sum over the rewards over the individual timestamps. So you can move the sum outside. You have the expectation inside. Once you have the expectation inside, what is that? Well, that's like just like what is the probability distribution over the current whatever. Like it could be the prefix of the trajectory if you have history-dependent trajectories, or sorry, if you have history-dependent rewards, or if the reward only depends on the current state action pair, then of course the history doesn't matter. Then it's just an expectation over the distribution of the current state action pair for that timestamp, right? So this is what's crucial here. Anyways,
Hey Chaba, I just wanted to ask something that you started off with earlier. So you mentioned there was like these 3 settings, right? There's the infinite horizon with discounting, there's infinite horizon without discounting, and there's finite horizon without discounting, obviously.
And there's also average score or average reward, but
yeah.
Yeah.
And right. And then you started talking about that the fundamental theorem that you proved in the lectures was specific for the infinite horizon with discounting. And then I didn't quite get, you started mentioning that you would want then to have a fundamental theorem for each one of these other settings. Did you say that this exists for each one of these other settings and it's just harder to prove, or will you talk more about that?
Something similar exists, and in some cases you need additional conditions. So let's go one by one. So the finite horizon setting is fundamentally different than this infinite horizon discounted setting, because this infinite horizon discounted setting has this stationarity burned into this. And the finite horizon setting doesn't have it, because as you're getting towards the end of the horizon, right? Like imagine that like you have some problem where you can, I don't know, navigate some environment. And if you're running out of time, and so you don't have much time, but it would take more time than the time left to get to some big reward, you're not taking the actions that would try to make you go towards that big reward that's too far away, right? Like clearly, if you have a deadline, that's going to influence what actions you're taking. The optimal actions are not going to be stationary. They depend on time. You could also rephrase this by saying that, well, okay, you could add to the state a time index, and then you make everything stationary again. But it's just like reformulating. The fact is that if you have a stationary Markov kernel, you just have a Markov kernel, and you have these timelines, then this theorem, the way it is stated, is not really going to hold, because you need to define everything a little bit differently. So you have to define the value functions in terms of like how much time is left, or how much time have elapsed from the beginning of time, and then the corresponding theorem is actually even easier to prove. It's kind of like a backwards induction kind of thing, except that, well, the greedy policies in this case, because the value function is indexed by time as well, they are non-stationary memoryless policies, right? Because time is part of the state, if you wish. So they depend on the time explicitly. So that's the finite horizon setting. So you can see that, like, yeah, it's kind of like almost like the total reward undiscounted setting, and then you can kind of reformulate the two things. So the total reward undiscounted setting is quite delicate because like, how do we know that these value functions are even well defined? So like these values are finite, like maybe there could be minus infinity or they could be infinity. So there are all of these questions that arise. And so then people need to start to add additional conditions under which all these values are well defined. And this doesn't quite happen in the discounted case if you have finitely many states and actions, because then the rewards, the immediate rewards, like the range of them is bounded, no matter how they are set up. So the total reward is also in a bounded range. And so all the expectations are well defined. And you might think that, okay, like this is just like some mathematical like weirdness, but no, it's like when you have these infinite expectations, things are really not well defined. If you're thinking about like, what can I do with such a problem, you will not know what you can do. And a lot of people are spending a lot of time on reformulating problems when this would happen. So the classic example of this is the which paradox? The St. Petersburg paradox, right? Um, when you're offering a gamble, a lottery, to some person on the streets of St. Petersburg. I don't know why St. Well, I know because the people working on this problem live there. So the game is as follows. I'm I'm offering you this game. I'm going to flip coins. And if the first time a hat comes out for the case time step, I'm going to pay you 2 to the K dollars. And the question I ask from you, how much are you willing to pay for this game? To play this game with me? I assure you I abide to the rules. So can we do a poll here? I'm wondering how people will answer this question. Let's see. Activity. Poll. Okay, start a poll. Ooh, okay. What is the they're using these online tools in a very advanced fashion. Okay, so one answer is less than 1, maybe. Another is 1 to 2, another is 2 to 4. I don't know. And then you, I don't know. Would you pay more than $100? Okay. I started a poll. Can you see it?
Yeah, can you also just restate the question? I'm not sure if everyone got it.
Right. So I'm offering you a game, but it's not going to be free for you. You have to pay me upfront some fixed cost for me to play this game with you. If we agree, like you pay me, then I will follow the following rules. I will keep flipping a coin, and it's a fair coin. Don't worry about that. I'm very fair. The poll, it should be somewhere on your screen. Anyways, oh, lunch. Oh, there you go, I think. And so I keep flipping the coin, and if for the first time, a hat, like we are waiting for a hat to show up. If it comes up the first time, the first flip, maybe I pay you $1. If it comes up on the second flip, I pay you $2. If it comes up on the third flip, I pay you $4, and so on and so forth. Yeah, the 100 minus meant to be 100 plus, like bigger values than 100. And then the question is, how much money are you willing to pay to me to play this game with me?
Wait.
Yeah.
No, I think it's because of the speaker. Oh, can you guys hear me now?
I can, yeah, we can, I think.
Interesting. Oh no, I was just gonna ask. So on the third flip, I get $4.
On the first flip, what do you mean? Like, no.
The
Like,
first,
I flip, if it comes had,
you get $2.
you get $1.
Oh, okay.
If it's the second, then you get $2. It doubles. Like, the later you get the had, the exponentially more you get.
So it's 2 to the k minus 1.
Yeah.
Oh, not 2 to the k. Okay, thank you.
Well, it doesn't matter. It's like the difference should be a factor of 2.
So you still get a constant, right?
Just change it.
So far we got 8 votes. Please, everyone, just think a little bit. It doesn't have to be perfect. Just vote, and then I will ask people who voted different things to tell me why they voted the way they voted. I guess, okay, I should have, I think it's, my poll is not perfect. But it's okay. All right, so far we got 13 votes. Getting there, almost there.
Wait, where is the poll?
Uh,
I think it's in the
If
chat.
any,
This one?
no, all the way to the right. I'll also mute yourself.
Sorry.
do you guys all see it? All right. So Prabhat says check activities to the right of chat button. It's like the little playful thing icon, I think. All right, so we got 15 votes. I show you the results. So less than 1 got 3 votes. 1 to 2 got 3 votes. 2 to 4 got 2 votes. 4 to 100 got 2 votes. 100 plus got 7 votes. So I want to ask someone who voted, I don't know, less than 1. Why you did that? What's the justification? Oh, by the way, I might decide not to play with you if you are very cheap. Oh, I should have said that. I'm not obliged to play. But I said that it was obvious. Like if you're too cheap, we're not going to play. Anyways, so who said less than 1? Someone. There are no stakes. Just pick up. Yeah, Chiamin?
Yeah, I think I'm following the worst case analysis. So I don't want to
Very risk sensitive, right? Like
yeah.
never lose $1.
But I didn't heard you may not play the game. So if I play that, I may like probably I didn't get a chance to play the game. I may like
Yeah.
raise
So you
raise
probably
my
would raise. And to how much would you be willing to pay for the game?
I feel like I would not go with the expectations case, but because I like some kind of hate the the
The risk.
the in fact there's a very high probability I will lose the game in the very first field flips. So I think I probably played 1 to 4, the second or the third choices.
I see.
Just for
I see.
fun. Yeah.
So in other words, you're pretty risk averse. Muhammad Shabad?
Excuse me, how many times are you gonna flip the coin? I think I
Until we
didn't
get
hear.
ahead. Until we get ahead.
Until we get ahead. Okay, thank you.
Right. So by the way, I think someone actually wrote something about what's the expected value, what's the expected reward that you can gain in this game if I'm willing to play with you. So the probability, yeah, it's infinity, right? Because the probability that we end the game on the case trial is 1/2 to the power of k, right? And then this has to be multiplied with 2 to the k minus 1. So the k cancels. So it's like 1/2, but you have to sum this for all values of k from 0 to, sorry, from 1 to infinity. So it's an infinite value. Okay. All right, so Abdul is asking, if we get a tail, then do you still remember the number of heads previously occurred to calculate reward? Well, I remember how many timestamps, like how many coin flips I made. Like I'm counting, right? And I offered the game only once. I'm sorry. It's like life is short for Oli Reza. All of these are really good. So I also want to hear someone who was at the other extreme end, the 100+. So what was the reasoning there? Anyone? There were like 8 votes for that.
Well, if the expected reward is infinity, then you can never pay too much, right?
So then you would also go for $1 billion?
Well, you can win $1 billion in $1, right?
You can win infinite amount, unexpected.
If you follow the expectation, it seems like a good idea.
Okay. That seems pretty risky to me. So I think that like you understand that expectations work in ways that could be unexpected, especially if they are really large, right? And very like, okay, maybe the other important lesson about this is that just going for the expected return may not be the best thing. Like if you're in scenario like this, the St. Petersburg paradox, you probably not going to determine the fair price of this game based on expected value. But somehow you take the risk into account. All right. So what's the distribution? Yeah, like Prabhat says, what's the distribution of returns? Yeah, it's like,
You want to be like,
it's really skewed, right? It's like you get with very, very small probability, very large rewards. It's like a very bad distribution. The large rewards are happening with extremely small probabilities. All right. So undiscounted case, this weird stuff can happen that the return is maybe negative infinite for some policies. It's really weird if we talk about the undiscounted case, often we switch to cost because it's somehow more natural to say that like, okay, maybe all the costs are non-negative and like we just sum up all the costs until somehow like until infinity, and then okay, maybe we're gonna assume that all the cost is finite. If some of the costs are infinite, then weird stuff can happen. The cost would be negative infinite, or you could get positive infinity. Well, that would be like very unusual and a happy scenario, but that's usually not the case. Anyway, so the undiscounted case is not trivial because of this, and also, so there are these other. So for example, one way of dealing with this undiscounted case is when you have some goal states, which are absorbing states. And if you enter any of those goal states, then you stay there and you receive no further reward or cost. And so let's say everything is in terms of costs, then this is kind of like stochastic shortest path. And that's like a beautiful set of problems. I really like it. You want to minimize the total expected cost. And so that setting makes a lot of sense. If you put these additional restrictions, for example, one restriction I think would be that all policies are proper. So that means that they have, from every state, they can reach the goal state with positive probability, and all the costs are non-negative. And if you get to the goal state, then there are no further costs involved. Then the fundamental theorem is going to be true. So there are these cases which are the meaningful cases most of the time when the fundamental theorem is true. The case for the average reward setting or average cost setting is very similar. It's like it's a case-based analysis. All right, so that answers the question about I think of whether the fundamental theorem is really limited to the discounted case or it holds more generally. Like it like something like this is going to hold. Maybe you have to put additional conditions. The nicest thing about the discounted case is that, well, if you have finitely many states and actions, no further conditions are needed. If you have infinitely many states and actions, then this doesn't work anymore. Because then the reward may be unbounded. If you start to assume that the reward is bounded or the cost is bounded, then all is fine, no matter the number of states and actions. But if you have infinitely many states and actions, then very often you find that the natural choice for the cost or the reward would be that it kind of grows. So for example, these LQR problems, right? So you have an inner system that you're controlling. So there is a continuous state, a d-dimensional Euclidean state. And somehow you can stochastically control this dynamics. And the goal is to keep the state in the small vicinity of 0. So the cost is going to have two parts. One is measuring the deviation of the state from 0. And the standard way of doing that is by putting a norm or squared 2 norm, maybe matrix weighted squared 2 norm on the state. So you want the state to be small. So it's kind of like a regulation thing. It's like the state is already like, you know, it's when you apply this LQR kind of thinking, then you already did something to the system so that it makes sense to talk about regulating towards zero. So kind of like shift the origin to the point where you want, like you're controlling a thermostat and then you want 27 or like 22, maybe not 27, that would be too hot. 22 Celsius to be in the room, then you would shift the origin there, right? And then the deviation from that point is what is going to be penalized in the cost. And if the temperature becomes really high, this is unbounded. Okay, that's a little bit unrealistic with temperatures. And also, in general, this unbounded cost is not something that, I mean, it's a delicate thing because it's not real. It's never real. Like
Yeah.
you will not have infinite, you know, cost or anything, but the cost could be running away. And when the cost is running away, then maybe your system breaks. So it kind of expresses the view that if the costs are getting that high, then something's gonna break anyways.
Oh yeah, because I was even gonna mention, like for your total reward unbounded, if you only can, like, sure, if you interact with the system for an infinite amount of time, you would have an unbounded cost, but you most likely only going to be able to interact with the system for a finite amount of time, at least if you don't take this asymptotic view.
Right. So these are all kind of interesting and important points to keep in mind. We are kind of trying to model some set of problems with some mathematical framework, and this framework is not perfect. It's imperfect in many different ways, and we have to be super aware of that. Nevertheless, it seems that whatever algorithm typically you get from these, they are reasonable. So for example, this infinite horizon, it's like, yeah, like it's completely theoretical, right? Like it will never happen. It will never interact with the system for an infinitely long period of time. It will just not happen. So then why do we model that? Well, it's because the alternative is that you say that I model the finite horizon setting, and then it turns out that you need to pay attention to how much time is left. So the infinite horizon sometimes just expresses the fact that you don't know how long things are going to last. So the stochastic shortest path problem is nice in this way, because there you can imagine that, like, oh yeah, like if you have a really bad policy, then it can go around and around and around, never gets to the goal. Can take it forever to be there, but like it could finish. If it was a clever policy, it would finish in a finite amount of time. So that's maybe a little bit more realistic. But for a lot of other things, like, I don't know, this continuing applications like AI and whatnot, like you don't really want to set an a priori deadline for these systems. Because if you do it, then if the system takes that seriously, then it's going to say, oh, I'm odd and tired, and now I stop exploring. I can't do those things anymore. And it's like just, you don't want to start with that. But and also the solutions that you're going to get are going to be maybe awkward a little bit. Maybe that's not really what you want. The important thing here is that, well, these are models, abstractions of the problem, and they are ignoring aspects of the problem in various ways. So they're not perfect. So we can think a lot about how to solve these abstract problems, but yeah, it's also important to think about whether a particular application can be fitted into a framework like this. And Of course, strictly speaking, it never can. Nothing can ever be like, unless you're completely general. But yeah, that doesn't mean, I mean, like, it's like you try to abstract away the things that you think are not important. So that's how it goes. Anyways.
And just to clarify, so when we have like these infinite state space, the reward can be unbounded because we can just define a function that's like increasing with the state. Anything,
I mean, like for example, the states could be just like the integers, and then the absolute value of the integer could be the reward, and then the agent wants to see bigger and bigger states. Maybe if it's a cost, then it would want to stay around there, right?
Yeah, and so then when we like, I guess this may be a bit ahead, but when we introduce like function approximation, one of the like appealing things is that we can deal with these infinite state spaces, but then we have to make the underlying assumption that the reward is bounded so that we still have this, so we can still stick with these like memoryless policies.
There is something in between. So you don't necessarily need to assume that things are bounded, but then it becomes delicate. So people, rather than, like, there's so many things to pay attention to, and this is one of the things to pay attention to. And so if you have other priorities, then you might as well make the assumption that the rewards are bounded, right? It just simplifies your life. But at the same time, if you ever need to work out things for the unbounded case, the results that you had before may not be applicable, right? Like, for example, the fundamental theorem just doesn't apply in general.
Okay, and one more thing. And so the other critical thing is that we're assuming we know the reward and the transition model for these, like for the fundamental theorem, right? And if, like, let's say we don't know the reward, then these memoryless policies are not sufficient, right? Like a policy that takes in the history, which I guess is
in what way?
Oh, well, I guess because knowing the history of the reward seems like it would benefit you, right? If you don't know the reward model.
This is kind of, so what you're saying, I don't know whether it makes sense in the context of, of this theorem. This just talks about, this.
Yeah, I guess it's just the past state in action, right? The history.
It's like we're building up the foundations in a very slow way. So later on, when it comes to the learning, then we can start talking about these things. Actually, there was a question related to this that I will answer later. All right. So the questions, whenever you see a theorem, is always should be, why should we care? Well, the other question is like, are these conditions really necessary? And we talked about some of these and like in what way you can change things. And then the other is like, isn't this just too brittle? So the why should we care? I think I already answered. Well, no, I haven't answered it at all. Well, I answered it partially. Like, we care about this because it tells us that we can forget about the past and we don't need to remember time counter either. It's enough to think about memoryless policies and also deterministic memoryless policies. From this, you should conclude that that's the only thing that you care about. But from the perspective of just being able to achieve good value, memoryless policies are enough. This is one part that's important. The other part is that if it comes to solving an MDP, what are your options? If you have a finite MDP, you could list all the policies, knowing this theorem, you can list all the memoryless policies. That's a much smaller set than all the policies. All the policies would be an infinite, uncountably infinite set. You have stochastic policies, whatnot. It's just like big set. But here, the first part just says that you only have to worry about or implies that you only have to worry about deterministic memoryless policies because greedy, like you can always find a greedy policy like that. And you can list all of those, and they are a to the s. That's their number. And you could just like evaluate all of them and choose the one with the best altogether uniformly best value function. Now, of course, no one does this, although the policy search methods try to, like reason with the space of policies. So in a way, they are trying something like this. But they try to be more clever about the search, not just like list everything and then evaluate everything and then just choose the optimum. But the second part of the theorem tells us something important, which is that the optimal value function is the fixed point of the Bellman optimality equation, which we will try to use to our advantage to reduce the total cost of arriving at an optimal policy. And in a way, this equation is the basis for many of the algorithms and many of the ideas that are used in reinforcement learning. So it's super important. This is, in a way, Bellman's big idea. Like sometimes people say that, well, what is this dynamic programming? So the idea of dynamic programming is that you're breaking up a problem into subproblems, solve the individual subproblems, and compile the solution. So how do we see this from the Bellman optimality equation? Well, like solving the problem by part A of this theorem would mean that we just need to find this value function. We just need to find the optimal values for all the states. And so the second part says that the optimal value for a given state can be expressed in terms of optimal values of, well, it happens the same state and other states, right? So that's kind of like the reduction to other subproblems. So here, the subproblems are like, how should I act if the initial state was this? That's a subproblem. So, and Bellman's idea was to introduce these value functions that summarize the values and then just calculate the values, and given the values, then calculate the policies. So do the computation in 2 steps. All right, so that's why this result is pretty insightful and important. And then the last question, isn't this too brittle? So it only talks about optimality, and very often we will not be able to afford to calculate anything that's optimal. But it turns out that you can relax it, and there are ways of using this result that show that things are not going to be too brittle in a manner that makes this result useful. So it's not just about optimality. You could relax these things and you could say that, well, okay, if you have a value function which is close to the optimal value function, you take the greedy policy with respect to this, then that policy is going to be near optimal. So things are not breaking down in a sudden way, but there is a graceful degradation of the performance if you're imperfectly evaluating things as you will pretty much all the time. All right, so that's the summary. How long can you talk about the single line? All right. Now to the questions. So we got a bunch of questions. I tried to order them based on the number of votes they received. Prabhat, do you want to ask your question?
Yeah, sure. So, like typically when we, especially in papers and so forth, we have those 5 things that are used to define MDPs, like states, actions, transition, gamma, and then a reward function. But so then my question is, should we include the start state distribution, or at least the fact that it exists in the definition of an MDP? And so I know that you can perform the Bellman equations and Bellman updates and so forth without using the start state distribution. But I do think like if we're taking an MDP as a representation of whatever your world is, then it would be incomplete without the start state distribution. And I guess we could also argue that maybe you can't answer all questions about the MDP unless you also have a start state distribution specified.
Okay, the second part, I'm not sure I understand. So regarding the first one, I think what's important to keep in mind is that we're just building up things in a gradual fashion here. And MDP is like are defined in a zillion of possible ways. And depending on the author, they would include the gamma or they would not include the gamma. Maybe the transitions are going to be inhomogeneous. The start state distribution, I think that the first part of your question is that how important it is to have a start state distribution. But first of all, so this theorem, the fundamental theorem that we had, right? It's not dependent on any start state distribution. So if we defined MDPs with respect to start state distribution, then it would be really weird and awkward to state terms like that. So sometimes the answer to these questions is that we're just like tweaking these definitions until it allows the best compressed representation of the ideas and results we want to give. So it's somewhat arbitrary. And you can see that like in the papers, depending on the context. Some people are going to include the study this distribution in the definition of the MDPs. I think in every such case, you should be thinking about, okay, like how important is this? Is this limitation? Is this, I mean, it's, when it comes to this learning context, or like you just want to get a good policy for an MDP, you want to have a good policy no matter what the state is, right? Like, so there is no start state there. But maybe this goal is too hard to achieve. And then you would introduce a start state distribution. But then we're losing a little bit of generality. So this is very often what happens in the papers under the hood, which is okay once you prove that without the start state distribution, the problem would be just too hard. And okay in the sense that like in a bunch of applications, maybe the start state distribution is not so hurtful, although a lot of people would disagree with that, and I would think that like you should really not think about a fixed start state distribution and finite horizon settings and like all of these, because they are interested in problems where, so for example, robotics, where you can't really reset or control the initial state, or any other application where that is the case, like no matter what initial state you're thrown at yourself, you have to be able to act well. So in those cases, the start state distribution is not too natural. Yeah, I would, later on, we will deal a lot with start state distributions and finite, like committing all these things. But it's out of necessity almost.
Okay.
So the second part, I didn't understand why you're thinking that the start state distribution is really part of how the world works, because to me, it's not. I think it's a modeling approach or like attitude towards problems. So I like to think about that, okay, my robot should be doing the thing that it needs to do, no matter the initial state. Not just like with respect to some state. If I can afford to fix the start state distribution, it's awesome, and maybe I can exploit that with my algorithms. But wouldn't it be better to solve this harder problem where we don't need to do that, I think it would be better. The question is, can we? And in order to be able to ask this question, we should define MDPs without star distributions, because otherwise we just took out even the possibility of asking questions for MDPs without start state distribution.
So that's why I guess in the first part of the question I asked, or at least the existence of it, because I guess in some cases it might not be important, right? So in the first part of my question, I say, should we include the start state distribution or at least the existence of it? So how would we?
The existence of a start state distribution goes without saying, right?
Right.
So in a way, it's like it's superfluous. Like, how would you modify the definition? You don't need to modify the definition. You can just say, okay, I want to deal with any start state distribution.
Okay, so it's safe to say that a start state distribution does exist. Whether or not it's useful is dependent on your problem setting.
I mean, you're asking the question whether a distribution exists over some set, and of course, unless the set is crazy and it doesn't have any structure, it does exist, right? There are many distributions. Like, we are just dealing with finite sets, so there are no measure theoretic issues here. So if you have finite state space, well, you can take whatever distributions over this state space, and they all exist. They are real, right? Like, they're just distributions over states. They do exist.
Okay.
Yeah. All right. Someone was trying to comment. If we treat an episodic problem like a continuous problem, then does it make more sense to have start state definition in MDPs? Well, for episodic problems, well, it's independent. I think it's independent. Like, you can always. I think that there is the other more interesting question of, like, okay, if we prove a result that applies for a fixed start state distribution, does this result imply that things also work no matter the start state distribution? Sometimes the answer is going to be yes. Anyways, we are jumping ahead with this. So let's move on to the next. Gabor, do you want to ask your question?
Yes, I asked this question after watching the videos, and then I read the lecture notes where it was said that we will talk about this later. But yeah, I was just curious how people in neural theory think about the average reward setup, because I only just heard it in like empirical circles, and I'm just curious what the status is right now. What do you think about it?
So there's been a lot of things spat on the average reward case, mostly in the control community. And the area community is less inclined to work on the average reward setting. And I think it's just like a question of, I don't know, taste and biases and history. And also because I think it's not trivial whether the average reward setting is actually, like, how reasonable that setting is. So you might have heard about, like, weird things, like that in average reward case, you could have policies which delay indefinitely starting to take the good actions. Because if you delay that, like, just for a billion number of time steps, your average reward is not going to be hurt, because for the rest of the infinitely many time steps, you're going to act optimally. So you're still optimal, but that kind of is weird. And it's, we want to, if you're working on the average reward setting, then somehow you would need to answer to this question of, like, why is this not going to happen? So if you only prove that your policy has a near optimal average reward, maybe it's going to do this weird thing. So because of this, most theory people not even start on this. Well, at least that's me. Maybe I shouldn't say that. I have no idea why others, but like for me, like I would need to think more about like what's happening here and why our algorithms are not exposed in a bad way in this setting. But at the same time, whether it's promising or not, I think it's promising. It's curious. It's interesting. I also think that maybe the total reward and just you want an algorithm that works no matter what the horizon is. So a horizon-free total reward algorithm is the real thing, especially if you're learning online. If you're in an online setting, I have no doubt in my mind that that's the real setting. The way you analyze these algorithms is oftentimes through the average reward setting, but that only comes in the analysis. And like, okay, maybe the algorithms itself use some properties of the average reward, Bellman optimality equations, and like, okay, so it's like, it becomes quite interesting. But in those analyses, when you're proving these results for the online case, you're proving something much stronger than just to say that in the like you're gonna get near optimal performance for the average reward setting, because that's just too big. So in a way, it's kind of interesting. It has interesting structure. But I think that the most practically relevant part of it is just like the total reward part. That, like you want this learning algorithm to go in a word and then just learn and collect as much reward as it can over whatever horizon it is going to work on. So if you want to prove results like this, so that's the online learning setting, very often you will end up with the average reward setting as a result of this, like requiring some analysis that involves the average reward MDPs, and then you do that. But yeah, so because of this, I think it cannot be neglected at all. And there are a lot of open problems. So later on, we're gonna talk about some of these algorithms which we can show that they work for the discounted setting, but there is like even phrasing the question. I think one problem is that for planning. So here, online learning means that you account for the rewards that you collect as you learn. And planning just means that you're interacting maybe with a simulator. And after you decide that you have a good enough policy, you stop using the simulator. And then you output the corresponding policy. Then you may have a problem if you're only showing that this policy is near optimal for the average reward case, because maybe in the finite time performance of it is not good. But of course, most of the time it won't happen because of certain things. But like, yeah, this is the issue. Okay.
Yeah, thanks.
Next one.
Oh, hi. So I guess my question is basically the convergence rate of value iteration. And also, Vlad raised a really good point about the alignment of occupancy measure and the reward vector. So I also wanted to know about that.
All right. Okay. Thanks. So this first one. So I don't know about Vlad's question. So maybe Vlad can ask his question. So this log 1 over epsilon. So maybe you jump ahead, you see that value iteration converges at the geometric rate. So that means that the distance to optimum is decreasing in a geometric fashion. So another way of expressing that, if you kind of like ask the question, how many iterations do I need for the error to decrease below an epsilon level, then the answer is going to be logarithmic in the inverse of this desired accuracy, right? So that's the answer to this question. It's just like inverting this geometrically decreasing errors, right?
Just a follow-up question on this. So basically, in this case, the value functions will be like a Cauchy sequence, right? Because they are getting closer and closer.
Sure, they're converging to the optimal value function. But we also know more. We know that they're converging geometrically fast. So that means that the distance to the optimal value function in the case iteration is going to be some number raised to the power of k times some initial value. And that number is smaller than 1. So therefore, like this distance is decreasing right, extremely fast. And if you try to invert this, you ask like how big k should be so that this error is less than an epsilon, then you get this log 1 over epsilon. Does it make sense?
Yeah, thank you.
Okay, yeah. So I don't know. I think we should save Lot's question a little bit later.
Yeah, I was gonna say I have like a pretty detailed description on the Slack channel that you can look at after the class. So
okay, great. So Yongchan, do you want to ask your question?
Yeah. So my question is for the memoryless policy, there's a sentence in the notes that saying that there are non-memoryless policy whose value function cannot be reproduced by a memoryless policy at every state. But I'm not sure how to understand this. So I'm wondering, like, could you give a example of such thing?
I'm pretty sure I can give you an example if I wrote this. Not off the top of my head. So I don't remember the example, but I suppose it will be some two-state, not too big MDP. So what's important to pay attention to here is that the value function has to be reproduced at every state. So you can reproduce the value with respect to a fixed state, but you can't reproduce the values at every state. But this doesn't apply, this result doesn't apply to the optimal policies. So, right, like these are irrelevant policies that have bad values that cannot be reproduced by memoryless policies. So we don't actually care that much about this. but you can construct examples. Right? So it's kind of like a very nice coincidence that, okay, like memoryless policies are not sufficient to reproduce the value function of all non-memoryless policies. And also, like if reproducing means reproduce it at every state, like at the exact same way. But this is completely irrelevant if we only care about optimal policies.
Okay, so is this for MDPs?
Yeah.
Okay. I was saying there's always the example of like a policy that has to take the same action till the goal state and then cannot be reproduced by a memoryless policy.
This is a memoryless policy, no, Alex?
No, it has to take the same action till the goal state in the sense that like if it ever
it remembers the first action it took or something like that?
Yeah, like it only gets a reward if it only goes left from the goal state. And ever veers off, it gets a smaller reward, and it can't remember why.
Yeah, okay. But like, okay, so that's right. But the example could be something like this, what you say, even in an MDP.
Yeah.
Like you could have a policy that kind of remembers what it was doing, and then like it kind of makes the value really bad for some things, but like it doesn't matter. Okay, make sense?
Yeah, thank you.
Okay. Prabhat again.
Yeah. So in the Sutton and Bartle book, they define reward functions using a state, action, and a next state. I've seen other places just use the next state for giving the reward, and sort of in our notes we use state and action, although we use the subscript. And so yeah, my question, it's kind of vague, but does this make things okay mathematically for most, I guess, theorems and statements that we have to use any one of these formulations for reward? I do know that sometimes, depending on how you formulate reward, it can make changes in implementation, but I'm not sure from like a theoretical point of view.
Right. So the truth comes out now. So the formulation for MDPs that I was presenting with just this reward depending on states and actions is kind of like the minimalist, interesting formulation. Maybe you could say that the one where the reward depends on the next state is also minimalist, interesting, but I think that that's kind of like awkward, because if you want to formulate an MDP given this reward that depends on a state action and state actions with this other way, which depends on the next states, then it's going to be awkward. You have to introduce these after states, which are just like a shorthand for the state action pair that you took, and then you call that a state, and then you can create new dynamics for that, and like dummy actions, and like it's going to be awkward, but it can be done. So they're like by and large interchangeable. But the truth is that there are some big differences. So what's important here, what came up earlier, is that the reward cannot remember the past. So it's like we don't allow past dependent or trajectory dependent rewards, like history dependent rewards. And you could add, I don't know, well, you can't really add further states down the line because you don't know how you're going to act. So that's like what stops you from adding, like S double prime, which would be the state two time steps from now. But I think what's important here is that the reward for all these things to work, the reward has to be Markov. And here the most general definition would be if we have actually one probability kernel that takes a state action pair and returns an X state and the reward together, right? So that's a little bit more general than even the Sutton-Bartle formulation. The Sutton-Bartle formulation allows the reward to depend on the next state, but maybe you also want to have stochastic reward, which is stochastic in other ways than like what is implied, what is encoded in the next state, right? Like, so maybe you just want to add Gaussian noise, or like, because it is there in the system, Gaussian noise is there, like how would you model it? So that's the most general formulation. And yeah, so here what happens is that since we decided to deal with expected values, this randomness of the reward just doesn't matter anymore. And we can just take the expected reward given a state and an action, and even average over the next state. And that has sufficient structure to capture everything that's interesting.
So is it safe to say, like outside of the transition function, including the reward, that for like state action, next state, next state, or state action, that all of these, either you can like change the MDP slightly or just fiddle with the expectations and it tends to work out in general?
Yeah, exactly. And but what I'm trying to say is that for some of the results that are going to come, you want something more. You want stochastic rewards, which is none of this.
Okay.
So sometimes stochastic rewards are genuinely stochastic regardless of the next state. And you just observe. It's not important if we're not talking about, like learning about the MDP or learning about the reward or whatever. If so far the MDP, like we did as if like you're given an MDP with, I don't know, like as a mathematical structure, and you're just studying this mathematical structure. So here there is invariance with respect to all these differences. But when it comes to learning and then like gaining information, then the noise is going to matter. And there it makes a difference. So it's not entirely true that without loss of generality, you can just assume that the reward is only a function of the state and action. If you start to assume that, then you lose something.
Okay.
So some problems are hard for which the reward is stochastic, and not hard if the reward is deterministic. So this happens. So there is actually a strong separation between problems with generally stochastic rewards and deterministic rewards. I call these deterministic rewards. Right.
Thank you.
Yeah, you're welcome. Chairman?
Oh, yeah. In the review, we also reviewed the fundamental theorem, which indicate that the optimal value can be achieved by memoryless policies, and there should be no loss if we define the policies based only on those memoryless policy. So I was wondering why we didn't define the policy as the memoryless policy in the first place, and what are the benefits or intuitions behind considering the broader class of non-memoryless policies?
I think it's curiosity. So if you didn't define policies as possibly dependent on the history, you wouldn't be able to answer the question whether it's important to remember the history or not. You can only investigate this question if you define
Yeah.
things.
And
I think it's an important point that the Markov structure allows you to forget everything about the past if you know the state. Even in, I mean, like Markov chains, kind of the definition is almost like that, but here we have controlled Markov chains with these rewards, and it still happens. But this needs to be shown. It's not completely automatic, as you could have seen from the proof. It's not necessarily that, trivial. And so the other part of your question is like, okay, but then papers are defining things only for memoryless policies. Yeah, I don't know. I think that they do that for the sake of simplifying things for the reader. Also, there is the related question of like, would you ever care about policies which are not memoryless? Well, all the learning algorithms are like that, and they're producing policies that change over time and like depend on whole history and like, so of course, yes. So even if you want to show that, for example, there is no learning algorithm that can do certain things, then you have to talk about this class of policies. So that's sort of implied, right? So for a negative result, you absolutely need to define this class of policies because the learning algorithms are a special case of these non-stationary policies. Or to be precise, a learning algorithm connected with an MDP gives rise to a non-stationary policy. Right.
So you're saying that in the learning process, the policy is non-stationary?
Yeah, I mean, like, think about it. So you update the weights of the neural network as you go. It depends on the history. So now you take an action that depends on the weight. So that whole thing depends on what you have seen before. So everything is non-stationary. And so if you want to theoretically study this and want to make claims about it, then it's unavoidable to define these things. Right?
Yeah, it makes sense that if we want to know the non-stationarity we have to first define it as like memoryless, oh, the memoryless policy.
Okay. All right. All right. So, Chi? Oh, we're running over time. I always think that the class finishes at 3:30. It's not. Okay, how many more questions do we have? Chiayi, Kushagra, Prabhat. Oh, too many. All right, so we can't do all of this. So I think we should just wrap up. All right, so I just answered this one. Kushagra is asking, if I'm not wrong, occupancy measure is something like the expected discounted number of times to visit a state action pair. Yes. That was easy. And maybe this is part of exercise proving a second theorem. Yes. That was easy. All right, so this, Rowan, do you want to ask your question? Because I wasn't quite sure.
Yeah, I think so from other kind of like sequential decision making, literature, I have found that at a decision point where we have to take some actions, we kind of denote our decision space as a probability simplex over the number of actions possible in that state or in that decision point. And here, since you're denoting like the set of probability distributions over actions, which are called policies, using this measure theoretic notation, I was wondering if there's like a
Fundamental reason for this? No, nothing. It's basically the same for finite.
Okay.
In that cases, they are the same set, right? Like if you have one thing, like if you have an element of one set, it's also an element of the other set, or induces an element of the other set, and vice versa. So it's like they're completely the same. I just,
Okay. Yeah.
since we are using this M1 notation already, why not?
All right.
But it's the same. Okay,
Thank
this
you.
is what I thought your question. Okay, so this could have been interesting, but maybe I just save this for the next occasion. So just 4 days ago, this blog appears on my Twitter feed, of course. I jump on it because I don't have anything better to do. And I read it. It's pretty nice. But then it discusses this simulation optimization, and it's quite interesting. I think you should read this blog post, and then we can discuss it the next time. Maybe can post this on Slack so everyone has access to blog post. All right. Okay. That's it for now then. Thanks for coming, and see you in 2 days.
Thank you.